In this example, we are just going to state the absolute and the local maximum and minimum values of our function, and we're going to be using this form, f of a equal b. So the first thing I'm going to look for is the absolute maximum value, and the definition for the absolute maximum is that the value f of c is an absolute maximum if f of c is greater than f of x for all x in the domain of f. Okay, that's more like the technical definition. An easier way to see it is it's just the highest point on graph. So that highest point would be c comma f of c, and then this value would give me my absolute maximum value. So if we look at the graph, we can see that this is the highest point on the graph, and it occurs at x equal 2. So f of 2 is equal to 3, and that is going to be my absolute maximum value. And you can see that this condition is satisfied because f of 2 is greater than or equal to f of x for all the other x values in the domain here. Okay, so let me write that down. My absolute maximum value or output is f of 2 equal to 3. Now my absolute minimum, similar to what I said above, the absolute minimum is going to be the lowest point on the graph. And we can see that's right here. And that occurs at x equal 4, and the value is -1. So the absolute minimum is f of 4 equal to -1. So now we're done with the absolute maxes and mins. We're going to move on to the local maximums and minimums, and these are a little bit trickier. Let me just quickly write down the definition. F of c is let's say a local, let's start with maximum if f of c is greater than or equal to f of x near c. Okay, so this is the part that's a little tricky. Near c basically means that for all the values to the left, for values, some set of values to the left and to the right, like an open interval, in other words, on an open interval that contains c. So just to show you visually, there is a local maximum occurring at 2. It's the same as the global or absolute maximum that we had. But the thing to note is notice how on both sides of x equal 2, my function is defined. You see a portion of the graph over here and a portion of the graph over here. So the function is defined on both sides of 2. In other words, in an open interval that contains 2. That condition is necessary in order to be a local maximum or minimum. So let me just write down that result. So I have a local maximum at if f of 2 equal 3. So these guys are really the same, right? And let's look for over here. This would be another example of a local, but this is the local minimum. You can see that f of -1 is less than or equal to f of x for all the x values that are near -1. So let me just write that down. And we can also just verify that my function is defined to the left of -1 and it's defined to the right of -1. So you can see that the graph has a portion on both sides of this point, -1, 1. Okay, and that actually takes care of all our local maxes and mins. So you're probably wondering, why is this not a local max or min? It looks like it should be a local maximum, right? Well, the problem we have is that even though my function is defined to the right of -2, it is not defined to the left of -2. There's nothing there. So there's no open interval containing -2 on which my function satisfies the condition that I need, which is that f of c is greater than or equal to f of x, and an open interval near -2. So this is not, and I'm just going to write that down for emphasis, is not a local max. And similarly, this over here, this f of 4 equal -1, this is not a local minimum, because once again, if I look at 4, my function is defined to the left of 4, but not to the right of 4. There's nothing over here. So it cannot be a local minimum. So I'm going to write that down again. Not a local min. So f of 4 equal -1. So that's probably the trickiest part about that, is recognizing that these guys are not local maxes or mins. But even though they're not defined on both sides, they can totally still be absolute maxes and mins, as you see in this case. So here's another example, and again, we're just going to look for the absolute and the local maximum and minimum values of this function, and we're going to put them into this form, f of a equal b form. So this is a simple example, but there are a couple things that are kind of tricky. So let's start by looking for the absolute maximum value. So that is also known as the global maximum, okay? So if I look at the graph, my eye wanders over here, but the problem is that there is an open circle, and that means that the point 3, 4 is not actually on my graph, which means that for this function, f of 3 is actually undefined. We can see that as my function the x values approach 3, so that the y values approach 4. So in other words, you could say the limit as x approaches 3 from the left of f of x is equal to 4, but f of 3 is never actually equal to 4, and that's why we have that open circle. So that's something to be careful about. What does that mean in terms of our absolute maximum value? Well, since our graph is approaching, it gets higher and higher, and these points are getting higher and higher, but it never actually attains this value. There actually is no absolute maximum value for our function. Okay. So let's take a look at and look for the absolute minimum value. So again, remember that that's just the lowest point on the graph. So my eye automatically gravitates towards this point. That looks like the lowest point, and it's not an open circle, so we're good. And that will be our absolute minimum value. And I'm going to write that as f of -1, which is equal to 1. So that takes care of our absolute maxes and mins. So let's look for our local values. So our local maximum and our local minimum values. So in this case, the only possibilities we could really have, we might look here and here, but the problem is, notice that my function is not defined on both sides of 3. So my function is defined over here, but there's nothing over here. So this can't be a local maximum. Same problem over here. The function is only defined on one side of -1. So again, neither of these can be local maxes or mins. So I'm just going to write no local max or min. In order to have a local max or min, your function has to be defined on both sides. So it has to have this kind of look, like it goes up and then down, or it goes down and then it goes up, or something of that sort, where your function is just defined on both sides of your x value. Okay, so we're going to do another example where we state the absolute and the local maximum and minimum values of the function using this notation. Okay, so in this case, let's start with looking for the absolute or global maximum value of the function. So my eye is immediately drawn to the highest point, which looks like it's here, but there's an arrow on the graph, which tells me that this graph keeps going up in this direction. And because of that, there is no absolute or global maximum. So let's look for the absolute minimum value of the function. Similarly, when I look for the absolute minimum, I'm looking for low points or the lowest point, which looks like it's this point. The issue I have, though, is this is an open circle. And what that tells me is that f of -2 is not defined. So as we approach -2 from the right, my function f of x is approaching -1, but it never actually achieves -1. So in this case, we would also have to say that as far as absolute mins are concerned, there are none. Next, I'm going to look for the local maximums. Remember that for local maximums, my function has to be defined on both sides of the x value. So I can't have any half graphs. What I need is I'm looking for kind of, typically I'm looking for like a hill or like a valley, or like something of that sort. This example is going to show us other things that might happen. So let's first recall the more sort of technical definition for a local maximum. So f of c is a local maximum value of f if f of c is greater than or equal to f of x for all x near c. And remember, near means the function has to be defined on both sides or in some open neighborhood of c. So if you look at this example over here, it does not immediately look like a hill or like a valley that we typically think of with local maxes or mins. However, if you look at this definition, if you think about, if we look at f of -1, we see that f of -1 is equal to 2, right? So f of -1 is equal to 2, and 2 is larger than any of the outputs if I look at values of my function near that result near -1. So this actually satisfies our definition for a local max. So let me write that down. That would be f of -1 equal 2. And like I said, even though it doesn't really look like a local max, it really does satisfy this condition that we have here. So let's take a look at, see if there are any other local maxes. So I'm also kind of interested in what's going on over here at this point. At f of 1, the value of the function is 1. So let me just note that here. And the thing you might notice is that our function is defined on both sides of 1, so it satisfies the condition that we need for local maxes and mins. And notice that f of 1 is equal to 1, and 1 is larger than any of the outputs I have down here, right? So f of 1 is actually greater than f of x. F of x for all x near 1. And that's true. And so that tells me that in this case, we also have a local maximum. So it doesn't, again, it doesn't look like a local maximum, but f of 1 equal 1 is also a local maximum. Let's take a look and see if there are any local minimums. And so let's see. If I look over the graph, I do not see any local minimums. This kind of looks like it would have been a local minimum, but the function actually never achieves that low point, and instead it pops up here and becomes a local max. So in this case, I would also say there are no local minimums. Okay,